Hello students, in previous class we discussed about laws of radioactivity and if we observe the laws of radioactivity, what we find? Generally radioactivity is a spontaneous process of emission of radiation, or simply we can say emission of some particles like alpha, beta and gamma particles. And when we observe the different type of emissions like alpha, beta and gamma, we find alpha emission causes a nucleus to reduce its atomic number by 2 unit and its mass number by 4 unit, whereas the beta radiation causes the nucleus to reduce to increase its atomic number by 1 unit and the mass number remains unchanged. And the emission of gamma radiation only takes place when a nucleus from any excited state jumps to ground state. Okay, and we find the mathematical form of laws of radioactivity as the rate of disintegration, that means we can say that the rate of disintegration, that is dN upon dt, that is the rate of disintegration. The rate of disintegration is directly proportional to the number of samples on decade at the time of measurement, and there is a negative sign, and that negative sign signifies that the sample from the nuclei continuously decreases with increase of time. Okay, and when we solve this equation, then what we find? dN by dt equals to minus lambda n, and lambda is called decay constant or disintegration constant. Okay, and further solving we find n equals to n naught e to the power minus lambda t. Okay, n naught is the total number of samples present in the nuclei, n is the total number of samples present at any time t. Okay, and lambda is the decay constant, and that is the mathematical form of laws of radioactivity. Okay, and if we draw the variation of number of samples on decade and time t with the time t, then we find the radioactive decay law exponentially decreases. Okay, exponentially decreases with increase of time. Okay, and if we take the similar type of variation like for the activity, simply we represent activity as R. So you can say in terms of activity, that is in terms of activity, R equal to R naught e to the power minus lambda t. Okay, this formula help you in probability calculation or in entrance exam. Okay, R, that is the activity at any time t, R naught, that is the initial activity, and lambda as usual as a decay constant. Okay, and when we want to calculate the mass of the sample remain on decade, we can use the formula m equal to m naught e to the power minus lambda t. Okay, so these two formula you have to remember, that means this will help to help in the entrance examination. Okay, this is in terms of activity and this one is in terms of mass, where m naught is the initial mass of the nuclei. Okay, so in this class we discuss about the decay constant and how can we define a decay constant, and what are the different significance of the decay constant, half-life. Okay, and what is the main physical significance of half-life. Okay, so if we observe this equation, law of radioactivity, okay, if we observe these two equations, from these two equations we can easily define decay constant. Okay, so now let us take a review. So decay constant, or simply we can say disintegration constant. Okay, and it is represented as lambda. Okay, So if we move towards the definition of loss of radioactivity, what we find? Rate of decay dN upon dt equals to minus lambda n. Okay, and as we define, lambda is the decay constant. Okay, so that means we can say lambda equals to dN upon dt whole divided by n. Okay, so this is the one form of decay constant, and as we discuss dN upon dt, that is the rate of disintegration, and n is the number of nuclei or number of sample present at any time of measurement t. Okay, so here we can say the decay constant is, or the decay constant may be defined as the ratio of rate of disintegration to the number of samples present at any time t. Okay, again I repeat, decay constant is defined as the ratio of rate of disintegration to the number of samples in a nuclei remain undecayed at any time t. Okay, so that is the one form of decay constant. Another form of decay constant can be obtained from the laws of radioactivity, last expression, and as per laws of radioactivity, what we find? N equal to n naught e to the power minus lambda t. N equal to n naught e to the power minus lambda t, and if we observe to this term, and if we take the observation upon this term, what we find? If we substitute small t, that is the time of decay, okay, small t as 1 by lambda, okay, time is equal to reciprocal of decay constant, then what we find? N equals to n naught e to the power minus lambda into replace t by 1 by lambda. Okay, so n equals to n naught e to the power minus 1. Okay, so that implies to n equals to n naught by e. So that is one form of representation, and if we substitute the value of e, that is value of e is 2.718. So what we find? N equals to n naught divided by 2.718, so that equals to n equal to 0.1 by 2.718, that variation will be 0.368 n0. Okay, so here we can write n equal to 36.8% of n0. What does it means? What is the meaning of n equals to 36.8% of n0? That means we can say here, if we replace t by 1 by lambda, but what we want? We want to define lambda. So here we can also write lambda. So what we get? T equals to 1 by lambda, or simply I can write lambda equal to 1 by t. Okay, so decay constant is just reciprocal of time. Okay, decay constant is a reciprocal of time. Okay, at which 36.8% of sample remain decay from its initial value. Okay, 36.8% of n0, that means the time or the decay constant is the reciprocal of time during which 1 by e, here that is we can say n equal to 1 by e times n naught, or simply 1 by e value is 0.368 or simply 36.8%. Okay, so the decay constant is the reciprocal of time during which the number of samples in a given nuclei reduces 36.8% of its initial value, and initial value is n naught. Okay, again there are two types, that means we can say one variation is 1 by e, or simply 1 by e value is 36.8%. Okay, so the 36.88% will be obtained when we replace n equal lambda equal to 1 by t. That means the decay constant is the reciprocal of time at which the radioactive sample reduces or decayed 36.8%, or simply we can say 1 by e times, okay, 36.8% of its initial value, and the initial value is n0, okay. So there are two different definitions. One is decay constant lambda equals to minus dn upon dt divided by n, okay, or simply we can say that will n equals to 36.8% of n naught, and this will happen when we substitute lambda as 1 by t, okay. So here decay constant is the ratio of rate of disintegration to the number of samples remain undecayed at any time t, or we can say decay constant is the reciprocal of time during which 36.8% of the sample remain decayed from its initial value, okay. So these are the two different form of decay constant, okay. So here there is one relation we find, that means we can say so now discuss the physical significance or main the significance of the decay constant, okay. So significance of decay constant, okay. So we can say the mainly there are 3 to 4 significance. First significance we can say decay constant is the characteristics of radioactive substance. That means we can say it measures the rate of decay of a radioactive sample, okay. Second things we can say it determines the rate of decay of a radioactive sample, okay. In the radioactive sample simply we measure lambda equal to minus dn by dt divided by n, okay. So decay constant measure the rate of disintegration of any radioactive material or radioactive nuclei, okay. Third thing so we can say the value of lambda, okay. If we measure the value of lambda is small, okay. If decay constant is small, then the decay will takes place slowly, okay. That means we can say the rate of decay is slow if decay constant is small, okay. Because here we can say the variation relation dn upon dt equals to minus lambda n, okay. So from this relation if we measure the rate of decay depends upon the decay constant, okay. And if the decay constant is small, then the rate of decay will slow, okay. And if decay constant is large and the decay constant is large, then we can say the decay will takes place very fast, or we can say that is rate of disintegration will be very fast, okay. Secondly, we discuss about the half-life. So simply we represent as T half, okay. What is half-life? Okay, or simply we can say half-life period of a radioactive sample, okay. So let us take a short example. Suppose a radioactive nuclei has 1000 number of samples inside it, okay. That means we can say there are 1000 number of alpha, beta, gamma radiation or gamma particles exist inside it, and during the radiation or during the disintegration the alpha beta particles continuously emitted from that nuclei, okay, and the disintegration proceeds, and we reach a state at which the number of sample inside the nuclei, suppose from 1000 to reduced to 500, okay, from 1000 value the number of sample reduced to 500, okay, and the time at which the number of sample reduced to 500 from 1000, okay, the time at which the number of sample reduced half of its initial value is known as half life, okay. That means we can say, if we take the initial sample inside the nuclei is 1000 and it reduces to 500 in suppose 10 second, suppose in 10 second the number of samples from 1000 reduces to 500, and during that process the time is 10 second. So we can say here the reduction is half, so sample will be half, okay, from 1000 it reduces to 500, and during this process the time interval is known as half life, okay. Half life is the time at which the radioactive samples remain half of its initial value, or we can say 50% of the sample decayed, okay. So half life we can say the time at which, okay, the time at which 50% of the sample decayed from its initial value is known as half life. Understand? So we can say the time during which half of the radioactive sample, half of the radioactive sample remain decayed from its initial value is known as half life, okay, and it is denoted by T half, okay. So generally we represent the half life as T half, or that is the called half time of the sample, okay. So from the radioactive law, what we find, n equals to n naught e to the power minus lambda t, okay. N naught is the initial amount of sample inside the nucleus, and n is the number of sample after some time t, okay. So if we substitute, if we take small t, that is the time equals to t half, okay, the time interval is half. That means we can say at t equal to t half, the number of samples n will be reduced to half, or it will be reduced to 50%. So initially t value of the sample is n naught, at a t equal to t half, number of samples remain decayed will be half, so n equals to n naught by 2, okay. So when we take time period is equal to half life, then number of the samples reduced to 50%, and initial sample will be n naught and it will be reduced 50%, that means it will be half. So remain will be n equals to n naught by 2, okay. So substitute these terms. So here if we substitute n by this value, so that is n naught by 2 equals to n naught e to the power minus lambda, t will be replaced by t half, okay. So that will give, cancel n naught and n naught, so that will be 1 by 2 equal to e to the power minus lambda t half, okay. So if we simplify this expression, So there is a negative sign and here is the reciprocal term. So we can say e to the power lambda t half equals to 2. Okay, reciprocal means here we can say 2 to the power minus 1. So both side negative power will be cancelled. Okay, so that implies 2. So replace exponential by logarithmic or take simply antilog on both sides. So lambda t half equals to log 2. Okay, and value of log 2 everyone know 0.693. okay, so that implies to t half equals to 0.693 divided by lambda. Okay, so basically what we find, the half life of a radioactive sample is 0.693 is a constant value. So we can say t half is proportional to 1 by lambda, that is half life is reciprocal of half life proportional to 1 by decay constant. Okay, so that means we can say the half life of a radioactive sample is inversely proportional to decay constant. Okay, this formula is very important and this will helps you in the exam. That means in most of the exams, that means in your CBSE, CHSE or NCERT level question, you will find definitely there is a problem on half life period. Okay, so you have to remember that is t half equals to 0.693 by lambda, or simply we can say t half equal to log 2 divided by lambda. Okay, now if we take the variation of number of sample with the time of decay, how will it represent? Okay, so now take the variation of number of sample with the half life period. Okay, as we draw the variational curve for n equal to n naught e to the power minus lambda t. Okay, what is the variation? Suppose the variational curve will be like this and it will meet the x axis at infinity. Okay, so this is the time axis t. Okay, this is the number of samples, that is n. Okay, at t equals to 0, what is t equals to 0, this point at t equals to 0 the number of samples is n0. Okay, and as the time proceeds, number of samples remain decayed. Okay, and if we measure, suppose this is the half life, at t half the number of samples will be, so what will be the value of sample at t half? The number of sample will be n0 by 2. Okay, and from now this will be the initial value for the second half life. This one is the first half life of the sample. Now from this first half life there will be decay. Okay, and during the second half life, and for the second half life this will be the initial value. Okay, and for the second half life, that is we can say second half life 2t half, the sample will be decayed and the value of remain sample will be n naught by 4. Okay, that means again it half from its value, that is n0 by 2. Okay, and if we measure for third life period, okay, for the third life period the number of samples will be n0 by 8. Number of sample will be n0 by 8 and the time proceeds like this. Okay, so now for first half life period, or simply I write for first t half n equals to n0 by 2. Okay, for the same sample for second t half n equal to n0 by 4. For third half cycle n equals to n0 by 8 and so on. Okay, and if we observe there is a variation n0 by 4, that means we can say 1 by 2 power 2, n0 by 8. Okay, 8 1 by 8, that is 1 by 2 power 3. That means we can say here we can write n0 into 1 by 2 power 3, and 3 means third half life period. n0 1 by 2 power 2, 2 means second half life period. Okay, and if we proceeds for nth half life, okay, so simply n equals to n0 into 1 by 2 power n. Okay, n is the number of half lives. Okay, so there is an important formula derived from the variation of half life, and that formula is n equals to n0 1 by 2 power n. So n is the number of half lives, number of half lives. Okay, so simply anotherly we can write n by n0, okay, equals to 1 by 2 power n. n by n0 equals to 1 by 2 power n. This is very important. Okay, suppose anotherly we can say number of half life. Okay, so that is n equals to, suppose the total time will be t. Okay, inside t, that means the total reduction time of the radioactive sample is t, and inside t there are n number of half lives. So we can say total time of decay t equals to, if there are n number of half lives for the radioactive sample, then total time t equals to n half lives. That means we can say n into t half. Okay, so that implies to n equals to t by t half. So if we replace here, so what we find, n equals to n by n naught equals to 1 by 2 whole to the power t by t half. Okay, this is also another formula, and that will help you for the problem. Okay, so there are 3 different forms of the radioactive variation. N equals to n naught, 1 by 2 whole to the power n. N is the number of half lives, or n by n naught equal to 1 by 2 power n, or simply we can say n by n naught equals to 1 by 2 power t by t half. T is the time, t half is the half life, n is the number of sample at any time t, and n0 is the number of sample at initial time. Okay, suppose there are some problems in the exam, like suppose a radioactive sample has a half life 1600 year. Okay, so there are some problems basing on half life and decay constant. Okay, suppose we take a problem, find the decay constant for a sample having half life 1600 years. Okay, so generally always remember half life has the unit in terms of second, or we can say minute or year. Okay, like this. Okay, most oftenly in problems the half life time or unit of half life is given in year. Okay, and as we find t half proportional to 1 by lambda. Okay, decay constant is reciprocal of half life, so unit of decay constant is second inverse or minute inverse or simply year inverse. Okay, so we can say for the decay constant units will be second inverse or minute inverse or simply year inverse. Okay, like this. So let us solve this problem. Okay, find the decay constant for a sample having half life 1600 year. Okay, come to solution. If we take the data, simply here is the value is given is t half, that is 1600 year. Okay, and you have to determine the decay constant, that is lambda. Okay, so as we know, t half equals to 0.693 divided by lambda. Okay, so in terms of lambda, that is 0.693 divided by t half, and the half life is already given. Okay, so that will be 0.693 divided by 1600, and the total unit will be year inverse. Okay, you can solve this. Okay, so the problem, that means some problems depending upon the half life will be like this. Okay, let us take another example. Suppose we take another example like half life period of a sample is 3.82 days. Okay, there is also unit in terms of days. Okay, after what time will be the number of atoms? After what time will be the number of samples be reduced to 1/8 of the initial value. Okay, so this is the another type of problem. So what is given here? Okay, so come to the solution. So here given the half life of the radioactive sample t half equal to 3.82 days. Okay, and he says the number of samples or the time at which the number of samples reduced to 1/8 of the initial value. That means we can say, suppose after decay the number of sample will be n. Okay, and from n value, from that n value the number of samples decayed, that means n is the number of samples after decay in time t. That means number of sample left in the radioactive nuclei after time t. Okay, and we know the radioactive decay law, that is n equals to n naught e to the power minus lambda t. N equals to n naught e to the minus lambda t, and lambda is the decay constant, and the decay constant can easily be calculated from the value of half life. Okay, but another data is given, 1/8 of the sample will be decayed from the initial value. That means we can say n equals to n naught by 8. Number of samples remain undecayed or number of samples reduced. Okay, number of sample decayed, that will be decayed in time. Okay, number of samples decayed in time t, that is n equals to n naught by 8. So that implies to n by n naught, that equals to 1/8. Okay, so simply we can say 1/8, that is 1/2 power 3. Okay, so here replace n by n naught equal to e to the power minus lambda t. So n by n naught, that equals to 1 by 8. So 1 by 8 equal to e to the power minus lambda t. Okay. So remove the sign, that is negative sign, and if we solve, that is e to the power lambda t equals to 8, take log on both sides, that is lambda t equals to log 8 with base e. So that implies to t, that is the time. Okay, simply log 8 divided by lambda. Okay, and if half life is given, then we can easily calculate decay constant, that is t equals to, so here you can calculate the value of decay constant, that is lambda equals to 0.693 by t half. Okay, so 0.693 divided by 3.82. okay, in terms of day inverse. Okay, and if we substitute here, that is log 8 divided by 0.693 whole divided by 3.82, and in solving we find that will be 11.46 days. Okay, so in 11.46 days the number of sample reduced 1 by 8th of the initial value. Okay, clear? N is the number of sample left, okay, after time t. Okay, number of sample left means we can say number of sample decay. केते decay हिच ताले को ताले decay ही गला केते 1 by 8th path decay हिच. Okay, so we can say n equals to n0 by 8, and this will be value at any time kete t. Okay, so if we substitute here, then we find t equal to 11.46 days. Understand? So these are the different types of problems arise in your board exams. Okay, I think everyone should be understand. Okay, thank you.